Welcome back to the deep dive. Today we are taking quite a fascinating conceptual leap.
We really are.
We're moving entirely past stationary charges, electrostatics, and plunging right into the world of magnetostatics.
Steady currents. That's the game now.
Exactly. Our mission, guided by the insights of Feynman, is to understand how these steady electric currents produce magnetic fields.
And, maybe more importantly, reveal something pretty fundamental.
Which is?
That the line between electricity and magnetism, well, it's often just about how you're looking at it, your perspective.
Okay, quite a claim. So where do we start?
Well, Feynman starts by defining the magnetic field itself, and you define it by the force it exerts.
Right, the Lorentz force.
Precisely. So if you have a charge tau moving with velocity dollars, the total force it feels isn't just the electric force.
There's extra bit.
There's a new component, totally dependent on its velocity. It's the magnetic force, Tuckenuller cross BR. That's QV times B.
Okay, let's unpack that Val dollar times B dollar term a bit. That cross product, it has very specific implications, doesn't it?
Oh, absolutely. That cross product is the definition of the magnetic field dollarize.
Right.
Because it's a vector cross product, the force that comes out of it, it's always perpendicular.
Perpendicular to what?
Perpendicular to both the charge's velocity dollars and perpendicular to the magnetic field dollar. Always. No exceptions.
Wait a second. If the force is always perpendicular to the motion, that means the magnetic field can steer the charge, right? Change its path.
Exactly.
But it can never speed it up or slow it down. It does zero work.
That's the crucial point. It only steers. It conserves the particle's energy. It bends the path. Think of particles spiraling in a magnetic field.
Yeah.
But it cannot add or remove energy. Any actual work done, any change in speed, that has to come from an electric field dollar.
Okay, so the B field is more like a guidance system than an engine.
That's a good way to put it.
Now, how do we scale this up? From one tiny charge moving to, like, the massive flow of charge in a current?
We need a way to describe that flow mathematically. So we introduce current density, the vector jaw.
Yeah.
If you have a bunch of charge with density jaw, and it's moving with an average velocity dollar, then the current density jaw is just rive times derived.
And it's a vector pointing in the direction of the flow.
Correct. It tells you how much charge crosses a unit area per unit time and in what direction.
And whenever charge is moving around, we absolutely have to obey the fundamental rule.
Conservation of charge. You can't just create or destroy charge out of nothing.
Right.
Mathematically, this leads to the continuity equation,
Well,
Vol.2 the tangent partial T.
which basically says,
If you draw an imaginary box, any net flow of current out of that box must be perfectly matched by a decrease in the total charge inside the box. It's like accounting for charge.
okay, so we have the force on one charge, 2v times b, and we have the description of flow, du jaw. Now let's connect them. What's the force on an actual current-carrying wire?
Right? Think of a wire segment, maybe length delta L is L, carrying a current dollar. That current is just loads of charges moving inside.
So we just add up all the tiny TTV times b forces on those individual charges.
Essentially, yes. And when you do that calculation carefully, the total force on that wire segment comes out beautifully simple. It's 1 and all times B times d delta L dollar.
A vector cross product again.
Always with the cross products in magnetism. And the force per unit length is even simpler. Just 1 and all D. This is the force that makes motors turn.
Now we're focusing on magnetostatics. That implies things are steady, not changing in time. What does that mean for the currents?
It's a crucial constraint. So the fields to be static, the currents must be steady. Mathematically, this means the divergence of the current density must be 0. Nidal J, do ever 1 are sick.
And what does Lablache equals physically?
It means the current lines can't just start or stop somewhere in space. They have to form closed loops. Think of a simple circuit. The current flows around and around. It doesn't just appear or disappear.
Okay, steady currents forming closed loops. Got it. So, under these conditions, what are the fundamental laws governing the magnetic field dollars?
There are two key equations derived from the full set of Maxwell's equations but simplified for magnetostatics. First, the divergence of bile is 0. Nebula at B equals 0.
Nabla at B equals BD0. What's the big takeaway from that one?
This is profound. It's the mathematical statement that there are no magnetic charges, no magnetic monopoles.
Unlike electric charges, where we have positive and negative ones that electric field lines can start and end on.
Exactly. Magnetic field lines cannot start or end. They must always loop back on themselves. Every North Pole has a South Pole somewhere. You can't isolate one. Nature seems to be built this way.
Okay, so nabla p psi b equals FSB tells us about the shape of the field lines. They're closed loops. What's the second law?
The second law tells us what creates the field. It's Ampere's law. In differential form, it's 2 Ciotala nabla times B equals J, epsilon Joule.
Right, the curl of B is related to the current density dd Joule.
Precisely. It basically says that electric currents are the source of swirling magnetic fields. If you integrate this law around a closed loop,
The integral form of Ampere's law.
yes, it tells you that the circulation of the B field around any closed path is directly proportional to the total electric current all dollar punching through the area defined by that path.
So current causes B field circulation around it.
That's the essence. Current is the source term for magnetic fields.
Okay, let's use that. Ampere's law must be useful for calculating fields in simple situations, right? Like a long straight wire.
Absolutely classic example. You draw an imaginary circular loop around the wire, centered on it. By symmetry, the B field must have the same magnitude everywhere on that loop and point tangentially.
Okay.
Ampere's law then makes the calculation trivial. The circulation is just mu dollar times the circumference,
Yeah.
$2 PRR, and the current enclosed is just all dollar.
So Euler times 2πrr is proportional to all.
Exactly. You find the magnetic field Bidal wraps around the wire in circles, and its strength falls off as 1 plus, inversely proportional to the distance Tidal from the wire. Beautifully simple.
And we use this principle, but maybe wrap the wire up to make controlled fields, like in a solenoid.
The solenoid is a fantastic application. You wind wire into a long coil, a helix, run current dollars through it.
What does Ampere's law tell us then?
If the solenoid is long and tightly wound, Ampere's law shows something remarkable. Inside the coil, you get a very strong, very uniform magnetic field, dolly dollars, pointing along the axis. And outside, the field is practically zero.
Wow, okay. So it contains the field very effectively.
Extremely effectively. The strength E dollar inside is just proportional to the current dollar and the number of turns per unit length, no doubt. This is how we generate controlled, uniform fields for experiments or technologies like MRI.
And it's worth remembering, as Feynman points out, that even permanent magnets, like a bar magnet, the magnetism ultimately comes from currents too, doesn't it?
Yes, absolutely. It's not macroscopic currents flowing in wires, but microscopic atomic currents. Electrons orbiting the nucleus, and even electrons spinning on their own axis.
Like tiny circulating loops of current.
Exactly like that. In magnetic materials like iron, these tiny atomic current loops can align with each other, and their combined effect creates the macroscopic magnetic field we observe. It all comes back to moving charge.
Okay, this brings us to what feels like the conceptual core of this chapter, the really mind-bending part.
Ah, yes, the relativity of electric and magnetic fields. This is where Feynman connects everything beautifully.
It's a genuine aha moment in the lectures. Let's set up the thought experiment.
Okay, imagine frame S. You, the observer, are stationary. In front of you is a long, straight wire. It's electrically neutral overall, but it's carrying a steady current of dollar.
Neutral wire, but with moving electrons making the current. Got it.
Now, next to the wire, there's a charged dollar, also moving, with velocity dollar parallel to the wire in the same direction as the current.
Okay, charge moving parallel to the current.
In this frame S, what force does the charged dollar feel? Well, the wire is neutral, so there's no electric force. But there is a current, which creates a magnetic field by $, and the charge is moving in that field.
So it feels a magnetic force. QV times B. Which way does it point?
Using the right-hand rule for the cross product, you find the force pulls the charge towards the wire.
Okay, in frame S, a purely magnetic attraction. Now comes the switch.
Now we jump into a new reference frame S. This frame is moving along with the charged dollars. So in frame S, the charged dollars is stationary. It's at rest.
The charge is at rest in S. What about the wire?
Well, the wire is now moving relative to the stationary charged dollars.
Okay, so if the charged dollars is at rest in S, its velocity is 0.
Right. And if its velocity is 0, the magnetic force term QV times B must also be 0. It cannot feel a magnetic force in this frame.
But wait, physics has to be consistent. The charge was pulled towards the wire in frame S. It must still be pulled towards the wire in frame S, mustn't it? An observer in S must see the charge accelerate towards the wire.
Exactly. The force must still be there. But if it can't be magnetic, what kind of force acts on a charge that's at rest?
An electric force.
It has to be an electric force, which means in frame S, where the charge is at rest, The wire, which looked neutral in frame S, must somehow appear to be electrically charged.
Whoa. How can a neutral wire suddenly seem charged just because we changed our frame of
This
reference?
is the magic of special relativity. It comes down to length contraction.
Length contraction from Einstein.
Yes. Remember, the wire in frame S had stationary positive ions and moving negative electrons. When we shift to frame S, the relative velocities of these positive and negative charges change with respect to our observer, who is stationary in S.
Okay.
Objects moving relative to U appear slightly shorter in their direction of motion length contraction. Because the positive ions and negative electrons now have different relative speeds in S compared to S, the spacing between the positive charges and the spacing between the negative charges will contract by slightly different amounts.
Different amounts.
Yes, because their relative speeds are different in the new frame. This tiny difference in length contraction means the density of positive charge along the wire no longer perfectly cancels the density of negative charge in frame S.
So the wire appears to have a net charge density just because of how we're moving relative to it.
Precisely. A very small net charge density, but it's there. And this apparent net charge creates an electric field, E dollars, around the wire in frame S.
And that electric field, E dollar, exerts an electric force, $5, ED dollar, on our stationary charge.
And here's the clincher. When you calculate that electric force, $5, caused by the relativistically induced charge density, it turns out to be exactly equal to the magnetic force, $5 equals a QV times B, that we saw back in frame S.
That is absolutely stunning. So the force is the same, but what one observer called a purely magnetic force.
Another observer moving differently calls a purely electric force.
Magnetism is just a relativistic side effect of electricity.
In a very deep sense, yes. They aren't separate things. They're two aspects of a single underlying electromagnetic field. How much electric field and how much magnetic field you see depends on your motion relative to the sources.
And Feynman shows this extends to the sources themselves, right? Charge density, $200, and current density, journal dollars, are linked.
Yes, they transform into each other under relativistic boosts. They are actually components of a single four-vector in spacetime, confirming they are fundamentally inseparable.
Incredible. Okay, let's quickly pull back and summarize the key laws for magnetostatics again.
We've got the two mainstays. First, the nabla CDA B equals a Dollar's law. No magnetic monopoles, field lines must close. Second, 2 under $1 noblo times B, epsilon dollar.
Yeah.
Ampere's law. Currents create circulating magnetic fields.
And importantly, if you have multiple currents, their fields just add up, right?
Absolutely. The principle of superposition holds perfectly. The total B field is just the vector sum of the fields from each individual current source. Makes calculations manageable for complex systems.
One last piece. The convention we use for directions. The right-hand rule.
Ah, yes, the good old right-hand rule. We need it because of the cross products, Euler times B for the force, and implicitly in Ampere's law relating d dollars and the curl of dollar.
It tells us which way the force points or which way B circulates around a current.
Right. But it's important to realize it is a convention. We could have defined a left-hand rule universe, and the physics would work, but our definition of the direction of Bile dollar would flip.
So B is kind of directionally defined by convention.
Feynman calls it an axial vector, or a pseudo-vector. Unlike a true vector like velocity or electric field, its direction depends on this chosen-handedness. A subtle but interesting point about the mathematical structure we use.
So what a journey. We started with the Lorentz force defining B, established charge conservation in steady currents, found the law Eigenrad-B and Ampere's law, saw how they lead to fields around wires and solenoids.
And then hit the major conceptual payoff, seeing magnetism as fundamentally a relativistic manifestation of electric interactions.
It really reframes everything.
It does. And it leaves you with a final thought, doesn't it? If the very nature of the force you measure, electric versus magnetic, depends on how fast you're moving relative to the charges, then how much of the physical reality we perceive, the forces we feel, the fields we measure, is actually intertwined with our own state of motion through space-time? It suggests a deep unity between space, time, and the fundamental forces, something to really chew on.
Definitely food for thought. Thank you for guiding us through that deep dive into the relativistic heart of magnetism.
My pleasure. It's fantastic stuff.
And thank you all for joining us. We'll see you next time on The Deep Dive.